This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good afternoon. Good to see you all again. So the subject is electronic system design. But then this subject is different from electronic circuit design in many ways. Content-wise, lab-wise, the way that you learned ECD is different from ESD. So this is a project-oriented subject. And when you come to the assessment, you will understand. So if you understand the project, then you are the master. So this is a project-oriented subject. And then whatever I am teaching is kind of adding to the project. So if project is a person, then what we are doing is we are kind of, nourishing the person. We are not adding the flesh. So what we are studying is the requirement for designing systems. So after attending this subject, you should be able to design complex electronic systems. So that is expectation. And definitely you will be able to design systems which I have seen. Because when I take some people for my lab, I interview them, and the first question I ask is whether you have taken ESD. Not because I taught ESD, because when you learn ESD, you will be able to design systems. Also, you will learn how to design a system. So that is a kind of a training plus knowledge. So you need a bit more training. That is the reason the lab will help you to get training. And then what I'm going to teach is essential parts of systems. But then I also will teach you how to think when you want to design a system. So that's what I'm doing. So towards the end, I'm sure that you will be able to design some complex systems. Then the project is DSO, digital oscilloscope. Then you might wonder, why do we need a DSO as an example? Because DSO is a complex system actually. Compared to simple system like measure the temperature in the room, you can make a system, but DSO is a bit more complex system. Why? Because in the DSO we have deliberately introduced some complexity. DSO itself is complicated. Why? Because DSO got a trigger part. So then you got some ADC, DAC, these things are involved, so that you are learning both triggering function. Then also there is a limitation for microprocessors or microcontrollers, that is speed. Then when you don't have enough speed, you will be using CPLD, something else. So all these things we combine together in the DSO. Don't worry about these terms if you don't understand. You will learn it on the way. So that you got only one project, that is a digital oscilloscope, and then you will be designing, and then we will send out your PCB for fabrication. Then you get a kit, the components kit, you have to solder it, and then we will give you some code, and then you can for the microprocessor, and then you don't have to write any code from the scratch. We will give you a code, and then you can modify the pins because you don't have enough time. Then we will give you some GUI, and then you have to show the DSO working. So that is a project. So last year we made some changes in the syllabus. Until last year I did not teach anything about DSO in the lecture, because that was the way syllabus was designed previously until last year. But then last year we changed it. So last year I taught entire blocks. Then last year I added more materials. Why? Because of you guys. You come to our lab for doing capstone and then didn't understand many concepts about the system. Some of the students made DSO working, but then as I said, DSO is a complex system. Even that student failed to answer some questions when I asked it. So that made me to think I should learn the blocks properly, and then I decided last year to include all the blocks, and I will be teaching extensively. So you are lucky, good that you took this year. So the students who took the subject a year before, this was not taught. Plus, there are a couple of extra lectures about the communication protocol, I2C, then SPI, TXRX, why these communication protocol. So these are not covered in the exam, but then these are some additional lectures. Again, because of you, some of you, when I asked during the capstone exam, why do we need I2C? We got SPI. Then they couldn't answer it. So that made me to think I took the blame on myself, because we are teaching you system design, and then I felt that I did not teach students these type concepts. So not in the syllabus, but I will be teaching. So I will be organizing some extra lectures, not examinable. Then by the way, good that I saw your ECD results, and I was very happy because so many of you got H1s, and the failure rate was very less, and well done. So timetable for this subject. So we have got only lectures on Mondays. I deliberately combined it because we got only around 22 lectures. So you don't have much to learn from the lectures. So you will be learning a lot of things from the lab. And so that for ECD, there are around 35 lectures. For this subject, we have got only around 22 lectures, examinable. And I combined it together. That is good. In the sense, when I teach some blocks, then I have to stop it otherwise. Then again I come back in the next lecture, then again I explain a little bit, I am losing the time. So better to combine together so that we have a continuity. And all the lectures are held here in this lecture theatre. Then labs. So your labs will be starting next week. That is week 2. That is from Mondays to Fridays. And it will be held in EDS rooms 10, 11 and 12. And I will be teaching this subject and coordinating. So you have got 4 lab tutors. w1l1, my PhD student, so he already did this subject. Again, Ski, he already did this subject. Yang, he already did this subject. Then Jason, he's also just finished his PhD. And then you also got a head of the lab projects. Sorry, I think this one is. Yeah, so Bryce. So Bryce will be overseeing all the labs because this is a complex lab. We need someone to organize the lab. So he will be overseeing the lab. So Bryce is my lab engineer, lab manager and electronics engineer. So you will meet all these guys in the coming days. So course content. So when you see this list, you will understand we are pretty much covering all the important concepts, but not in depth. So we will be studying everything from the system point of view. So introduction to system design is today's lecture. Then we will be studying about operation amplifiers, filters, data converters, oscillators, phase locked loops, PCB design, digital systems, power supply, isolation techniques, thermal analysis, test and measurements, sensors, batteries, signal conditioning and EMC and noise. So please note that these all are not covering one lecture, maybe some half lectures. So we will be understanding all these concepts from the system point of view, not in depth. Like phase locked loops could be one subject in some other university, you know what I meant? But then as a system engineer, we should be knowing all these important concepts. What is a phase locked loop? And then what we will be doing is we will study what is a phase locked loops. An example, I am taking phase locked loops. So what are the applications of phase locked loops? And then where it is applied. So that when you design a system, you know that, oh, that one we need to multiply the clock. Which system I should be using or which component? Yeah, I need a PLL, something like that. So we will be studying all these things, and most of the things are we already using in the DSO, the concepts. Then syllabus, focused on real world design challenges. So DSO design is a real world design. It's a project oriented. Teaching best practices for design of complex systems. So we will be teaching the best practices for design of complex systems. Then methods and approaches to tackling real world challenges. So after DSO, you will be definitely able to design very good systems. Labs. Most of the major learnings, designs and full hardware implementations happen in the lab. Lectures. So what lecture will be? Training students as a system engineer to broaden the key concepts. So you should know whether you are a system engineer or you are a circuit engineer. You will understand on the way. So this subject will help you to become a system engineer. So system engineering is a bit different from the circuit engineer. Course assessment, semester long project, 45%. So 45% is coming from your DSO. Final exam is only 55%. So this time you got more weightage in your pocket. So 45% is in your pocket. If you do project well, you already got 45. Sorry, not 45, only 40. Because if your DSO is working, if you answer the questions, you will get 40. The remaining 5% is set apart for innovation in your design. So what innovation you bring into the design? So then only you get the 5%. So 40 plus 5. Innovation could be improving some resolution. I will tell you example on the way. Some innovations people did in the last years, but then you can't use that innovation. If you are using, you should bring that into a new level. You know what I mean? Same innovation, we know that, okay, whatever I did, if you implement, that is not an innovation. But if you take into another level, yes, like somebody improved trigger function to some extent, and then you improve it to some other extent, that is acceptable. So then only you get the 5%. Then 55% focused on assessing theory relating to the design projects. Again, out of 55, around, I don't know, 20-25 is coming from DSO. So out of 55, there will be system level questions. We will ask you to design some systems. What are the block level diagrams? Maybe realize some circuit inside. Then there will be question from DSO, based on the DSO. So that may be another 25%. So in the final exam, there will be question from DSO, sure. You can see the past exams. And then there will be question from the lectures that is related to the system. Then hurdle requirement. So you have to pass the final exam to have a chance of passing the subject. Out of 55, you have to pass this hurdle. There is a hurdle in the final exam. So syllabus, again, open-ended project. So it's an open-ended project. We will give you specification to design the digital oscilloscope. So it's an open-ended, means you can add many functions to help you developing ability to self-propagate and introduce your creativity. The syllabus for lectures is deliberately designed by an electronic industry. So this syllabus is designed by an leading electronics industry in consultation with us to give only the required help for the project, that also at the initial stages. So the industry opposed to the idea that we will be giving all the information. So they said that that is not a good idea. But then we are still, giving a bit more information. The industry will be unhappy, but we are giving a little bit more information. So this is designed by an electronics industry. So they said, okay, after doing this one, definitely they will be useful to work in our industry as an electronics engineer or a system engineer. Most of the syllabus is designed to train and equip you as an electronic system engineer. So you have to understand what is a system engineer. So how to become a system engineer? Oh, how can you think that you are a system engineer? What are the attributes you should be having in order to become a system engineer? So as I said, based on the SES feedback in 2017-18, what I have done is some students requested fortnightly consultation to discuss only labs, because lab is complex. So we have fortnightly consultation. I'm happy to make it even weekly, only to discuss labs. So your tutors and I will be there. If I am not there, your head tutor or your one of the tutors will be there to help you. Any questions, your simulation or your hardware, any questions you can come and ask. Then more explanation of the oscilloscope concepts, means the block level diagrams, and some more explanation of the blocks, how it is working end to end. That I will be doing. Then showing a working board of the oscilloscope video. That also we will upload. I think it's already on the LMS as a working board. And what are the signals at the input, what are the signals are expected at different stages. Then more block level diagram explanation, because DSO got around 10 major blocks and then they connected together 10 major blocks, and then it is good to understand how the signal is propagating in each block. More explanation definitely I will be doing. More assistance in design and hardware implementation. So that's the reason we are giving more consultation. So if you struggle in any part, please write to me, so I will assign a tutor to you so that you can have more consultation. Then 2 to 3 extra lectures for teaching content related to labs. As I said, the communication protocol. Then I also will be teaching you instrumentation amplifier. Maybe you have not learned instrumentation amplifier. That is an important amplifier. So that these things will be covered 2 to 3 extra lectures. Project outline. So when you studied ECD, we have given you analog discovery. I know that you use an analog discovery, and analog discovery got 2-channel 100 mega samples per second 14-bit differential input oscilloscope. It also got 2-channel waveform generator, 16-channel logic analyzer, and spectrum analyzer, network analyzer, voltmeter, all these things in a small box. Now what you are going to design is only 1 channel, maybe 40 mega samples per second digital oscilloscope, maybe 8-bit. And then now you will appreciate analog discovery. You used it as a black box and then you maybe did not respect. Now maybe you will respect when you see analog discovery. Oh, such a great design. After you make your own DSO. And you can also appreciate the size. Everything is in this small size. And so for the ECD, we have given you oscilloscope. For ESD, we will ask you to make oscilloscope. So project outline. Build and test 20 megahertz USB digital oscilloscope. So this frequency we have not finalized because we change every year, design a little bit. We will post it on LMS. We will give you a specification. That's what we do. So we will be approaching a kind of a professional approach to the DSO project. We will give you the specification and you have to design the system meeting the specification, such as input frequency range, cutoff frequency of the filter, and impedance range. There are so many specifications. So you might have seen on LMS. We already put it on the LMS. And then we will tell you what is the frequency. Then filter, your choice of basic or advanced implementation. So there are some sections or blocks that you can decide how to proceed, like filter design. It could be passive, active. Then if it is active, how many orders? Second order, third order, fourth order, all are up to you. Then individual project. So it's an individual project. It's not a group project. A parts pack will be given. So you don't have to buy your components. You are welcome to source it if you can, but we will give you the parts kit. Then the waveform should be visualized via PC. So we will give a GUI. So you have to show the waveform of your oscilloscope. Then the requirement, Altium Designer 10 or higher. So we will be using Altium for designing the PCB. LT Spice, version independent. You should know LT Spice because we will be designing the front end simulation. We will be designing the front end using LT Spice and doing simulation. Then Atmel Studio 6 or higher. Terminal applications such as real-time, hyper-terminal or Arduino programming environment. Then processing 2, scripted programming environment for Java. So these are the software we will be using. The project specification will be available on LMS in the coming weeks, along with the design libraries needed to develop the schematics and PCB for your DSO. So you will get a design folder on the LMS. So you can download the design folder. That is a folder for the project. So references. So this is a system level subject. Unfortunately, we don't have a textbook. So that's the problem with the system level subjects. There is no textbook. So most of the lectures we developed from the white sheet, and then some we prepared by ourselves. And then if you ask the recommended text, maybe the art of the electronics. So that may be a system engineer must have this, the art of electronics. The art of electronics, you want to design a filter, then they will give you a couple of examples. So this is a filter, and then these are a couple of examples. You want to design some amplifier, then it will give you, this is the amplifier concept, and then these are a couple of examples. So this is a recommended textbook. Then if you look at the lecture slides, you will see a lot of online software link, website link, blogs, feeds, videos if you want to further learn it. Then we will be going to the system. So as I said, who is a system engineer? So that's a question. Again, system engineer, for me, if you design an amplifier, you are not a system engineer, because then you are a circuit engineer. Then who is a system engineer? Again, system engineer is kind of a little bit in a gray area, but then having said that, it is not a fully gray area. So somebody is making an end-to-end system. End-to-end system means there should be front end, there should be processing part, there should be storing the data or interface, kind of end-to-end system. For example, I want to measure temperature of this room. Then we will be designing maybe some thermocouple, then we got some amplifier, filter, then we are going to turn on some LED when the temperature is exceeding some, then we have a microprocessor, and then the LED. So that's an end-to-end. You know what I meant? So that's a system. Again, oscilloscope is a system, because oscilloscope is kind of a independent system that can give you something, like you can get the waveform and then you can see it, and that's end-to-end. Front end, then it got processing, it got display. So in the big companies like Agilent or somewhere where the oscilloscope is made, the oscilloscope is not made by one person. So they have got different groups, ADC group. So they will be designing the ADC part. So they are the circuit engineers. Then there will be front end people, amplifier, filter design people. Then there will be another CPLD or microprocessor, that part, interfacing group. Then all these group, they meet and then they come up, make the oscilloscope. So that is not an excuse for you to combine and then do the oscilloscope, because your oscilloscope is a simple oscilloscope. So that's how it is working. Then who is a system engineer? So usually a system engineer comes from maybe electronic system engineer comes from circuit background. For example, you are joining Agilent. When you join in Agilent, then they will put you in the maybe filter design group. So filter design means you will be only designing the filters. And then who will become the system engineer? The system engineer means you will design the filters, then you also will interact with other people, maybe they are the interface people. And then definitely you will be interacting, but if you study the interface, if you study the processing part, and then if you can connect all these things and understand the oscilloscope, then you are a system engineer. Then you will come up in the organization. So in the big organization, system level people will come up. So system level people, how you will become a system level people? So system level people means they have got a vertical growth. Vertical growth means you will be specializing in your area. If your area is filter amplifiers, then you will be designing very good filters, very good amplifiers. After coming to a particular point, you will become horizontal. So this is called T type of carrier development. T, we call it as T shape. T shape means you will be specializing, come to a point, then you will study the remaining blocks, and then you will understand end to end, and then you will become a system engineer. Then, so when you are a system engineer, somebody will come and tell you, I want to measure the reflectivity of that wood. Then if you are only the vertical guy, then you will say that, oh, I know that some amplifier is required, I can design the amplifier, but I don't know how to make the system. But if you again study the horizontal part, understand, then you will say, oh yeah, I am a system engineer. So how the system engineer will say that I will get a couple of guys, oh, he knows amplifier, he knows filter, I know what are the blocks required. And then I will immediately say, in order to measure how to think it as a system engineer, I want to measure the reflectivity of that wood. I need a source, one block. Then the source light is going and hitting, we should measure it. We need a detector. You know what I meant? Then you got a first block, source, then detector. After detector, we may need some amplifier. Then we need some filter. Then we need some ADC because the waveform you need to convert into digital. Then we need maybe some kind of microcontroller. Then we need some kind of storage system or a display. So I got the block level diagram. So I am a system engineer. You know what I mean? Then I will call, okay, you got a filter expertise. You please design the filter. You got ADC expertise. So like that, say system engineer means when there is a problem, the system engineer knows end to end the block. But his specialization may be in a particular block, but he will be able to understand other blocks. So the best example of system, because I come from a system engineering background. When I graduated like you, I joined in a group in the aerospace industry. And the satellite, I was working on satellite payloads. So that is one of the complex systems I have ever encountered, a satellite or a rocket. So that is the reason there is a term, it's not a rocket science, because that's such a complex system. Again, when it comes to satellite, it is very interesting. In our group, we were system engineers. But when we see the entire satellite guy, he is the main system engineer, we will become subsystem engineers. Because the satellite got a lot of complex systems, subsystems. And when I joined we went to the dining hall, then somebody introduced me as a new system engineer. But I didn't understand, what is a system engineer. Okay, then I shook the shake hand, and then later only I got the idea of who is a system engineer. So as I said, the system engineer means you should be knowing the end to end of whatever you are doing. If you are in the oscilloscope company, you know end to end as a block. When you hear the problem, you should be able to draw the block level diagrams, and then you should be able to design those. Or you find out the people who are expert, and then you should know what is the signal coming from each block and how it will work as a unit. Then you should have a specialization, then only you can come up as a system engineer. So complex example, I like satellite because of my background, the previous background. So in the satellite, so what is a system design? People might ask, what is a system design? So system design implies a systematic approach to design of a system. So we have a systematic approach. Systematic approach, as I said, we heard the problem, then we will make first maybe top level, block level diagrams. And then systematically we draw the blocks, and then we approach the system. The process of defining the elements of a system, such as architecture, modules and components, the different interfaces of those components and data that goes through that system. So that is a system. So for example, this satellite, as I said, the satellite is a complex system. In the organization like aerospace, if you go to Boeing or if you go to Lockheed Martin or Northrop Grumman, these guys, the satellite person means they don't hire anyone from other organization. They might, somebody may be coming from Boeing to Lockheed Martin, but usually they don't hire people horizontally. These people are just, came up from the organization. So they don't promote anyone as the top guy in the organization, except, it's not from government. Some government person might be the top guy, minister or someone or secretary, but usually the organization, the director of the center, they will be growing with the organization. So they know end to end of the satellite. Like when I met the director in the aerospace, and then he asked me which subsystem you are developing. Then I said, okay, we are developing some payload to measure the topography of moon surface. Then because I was new, so he just drew each block in the satellite. So whenever we went for the meeting, he could draw all the blocks, major blocks in the satellite, and say, this is a thermal system, this is the input, this is the output. So where your things are connecting, so he knows the end to end of the satellite. So that is a level of understanding people got. And then what we have designed is maybe only one subsystem, but then this subsystem is a system for us. So this is a system that can measure the maybe topography or reflectivity of some surface. And then systematic approach, how will you design it? So as I said, when you want to measure the topography, you need a source. See, that's what it's got, some laser source, and then it got collecting optics, then you got lots of processing, electronics, and some kind of storage, and then some kind of interface. So systematic approach means, see, this got so many blocks, and then this is one block will be designed by one big group. In this one big group, the system engineer will make this type block level diagram. And then they will say that somebody will be working on laser, somebody will be working on this power supply thermal interface, somebody will be working on this electronics, somebody will be working on this optics, somebody will be working on this attitude and position interface. You know what I meant? So this type systematic approach will be followed for the system design, and the system engineer will be drawing this one, and then allocate to different people. So that is the idea of system engineer. So when you are a system engineer, you should be able to draw the top level block level diagram, and then you should be able to understand, even if you don't know some blocks, but you should know what is the input, what is the output. You know what I meant? Because suppose somebody is using some complex control algorithm in a block, but then you don't have much expertise in the algorithms. You don't need to, but you should know what is the input, what is the output. Logically, you should be able to connect to your system and understand. So that's what the system engineer does. As I said, when I met the director, he knew the attitude control, he knew the power system, he knew the communication module. So he will draw one block, he will be drawing maybe 3-4 inputs and 3-4 outputs. And he knows that this is the input required, this is the output required, these are the voltage levels. Even he knows the thermal, the mechanical structure, what is the FEM analysis, what are the numbers accepted. Because otherwise when you launch, your resonance frequency should be much higher than the vibration frequency of the satellite. So he knows all these values, and then that is a system engineer. So he comes from maybe electronics background, so he knows the electronics maybe end to end, but he knows the other blocks, what are the inputs, what are the outputs, how to connect together. So that's how you should be also training as a system engineer. So UK, so this one I like it because I think maybe it's not volume. So this one, this link, I like it because this one is there is a small satellite. I think UK guys launched.
Writing's not that easy, but Grammarly can help. This sentence is grammatically correct, but it's wordy. And
see, when the UK guys, this one I like it because this is a very good example of a system. So you can see the satellite is a system, and then it's only 10 centimeter, 10 centimeter, and then 30 centimeter. Then you can see the subsystems, how they have designed. So they will be saying this is the entire satellite, and then they have designed each module separately. So you can watch the entire video later. See, this is maybe this is a subsystem, but then this is kind of a system because this is doing the complete thing. When you integrate in a satellite, this will become a subsystem. So this kind of this is a systematic approach. So they design each module separately and then integrate together in a systematic way. So you can watch it later. So system design overview. So when you say system design, you should have some ideas. So what are the things involved in system design? So design process. So every system, there are a couple of systematic approaches. So one is a system design process, then hierarchical design, documentation, design for manufacture, working with others. So these are the important things you should be learning as a system engineer. So you should know design process, designing the blocks. Then we will be approaching a hierarchical design. Hierarchical design means how you can make the complex things down into simple blocks and then design the circuits. Then documentation. Documentation is very important. When you work in an organization, most of the time, if you are in the R&D group, you will be preparing lots of documentation because company doesn't want to close when you are leaving. So they ask you to make lots of documentation. Like when we were working, I made so many documentation because once somebody is going, then they can continue the work. Plus, when there is an issue, they can trace it, even what went wrong. Then design for manufacture. So this is also very important. Your design should be able to mass produce. So this we have issue. So you might not appreciate design for manufacture until maybe you start a company or you encounter something similar. Because in our group, we started maybe 3 companies with students, and then we found out some of the designs are not suitable for manufacture, mass production. So we had to spend a lot of time, and then in some cases we also asked some engineering design firm to help us with this design for mass production. There are some engineering firms, they are specialized in modifying your design for mass production. Then working with others, as I said, when you are working in a system, then there will be a couple of different blocks, then you should be able to interact them properly, otherwise your blocks will not come together. So design process. So in the company what happens is the management, they might get a project, and then the clients will come, they will tell you the requirement. Then you will be writing down the specifications. Like for DSO, suppose you are designing a DSO for some clients, they will say that what is the cutoff frequency, what is the noise accepted, what is the frequency range, what is the input impedance. Then what the management will say, okay, you start the design, a system group. Then they will find out, usually in the management, they will ask how much budget is available. Then they will compare the budget allocated with respect to the specification. So that's how the companies they do. They don't simply get some specification, like you are designing, as I said, we are in the company, some client came, and then they said we need to design the DSO. These are the specifications. Then I will ask how much you will give. They will say that, okay, we will give you 5K. Then we will check whether within 5K we can design or not. Then if not, we will go back to the client and say, no, 5K is not sufficient. With 5K we can give these much specifications. So we always compare the budget. Then again we modify the specification. Then we will do some research. What are the components available? What are the designs in the market? We have to study. Then we come up with a very good design. So this research part is important. Even in your capstone project, there are many things already done in your capstone, some algorithms. So you can actually search and read the paper and then implement them. So that's the reason the research part is important. So capstone also is a very good example of designing a system, because you are designing an end-to-end system. And then endorse the design, or you model. Then if the design, then they model it, simulate it, and then there is some engineers, they sign off, design sign off, and then it is fine. Then if it is design sign off means if these things, when you do it, some issues, then again you come back to the budget, because then you understand we need some more stuff, and then this will go in a loop until it is the final one. Then after you model, simulate, design or validate, then you develop the prototype. Then you evaluate the prototype, and then after prototype you will redesign or modify. After testing you will find out, oh, there are some issues, then you will redesign, modify, and then maybe you again go to the budget and check it whether enough budget is there, and then again you may change the specification and then come here, and then you go for the manufacture production. So usually in the company they will be making at least one prototype and then meeting all the specification, and then they will test it thoroughly and then find out the issues. Then they will again come back to the design, and again they will be doing the system. An example is a capstone project. So many capstone projects, maybe I supervised more than 30 capstones in my last maybe 4 years since I joined at UAM. So some of the capstone projects are kind of this is following this process. So we have got, for example, one capstone from a post office for designing an adaptive photography system, because when they take photo in the post office outlet, there is an illumination problem because of the environment changes. So then they asked us to develop a system. Definitely we offered as a capstone project. So developed a system that takes a photo and then do the image processing, and then they find out the shadows, and then they find out they made LED array, and then each LED is 8-bit and then illuminate accordingly. So then they made, in the first year they made a prototype, and then they tested. They found out many issues. Second year again we offered a capstone. Then again they started to fixing that one. So it is going on in different loop. Second year again they tested some issues, and then still redesigning. So that's how it will be in a capstone. Also some ongoing capstones are example of this design process. So design and verification, that is very important. That's the reason the DSO, after you design the DSO, we will be checking your DSO with respect to the specification, how much you met it. Because that is a kind of evaluating the proper engineering evaluation. Then if you go to space industry, aerospace industry, they will make one more in between. So they will make a prototype, and then they will test extensively, and then they modify the design if it is not meeting the specification. Then they will make an engineering model. It is called engineering model. That is only in the defense and aerospace they follow the engineering model. Engineering model means when you make the prototype, you will be using the normal components. But for aerospace and defense, you need military 883 components. If it is for space, you need classes components. That is radiation hardened. Then you will not straight away make the prototype with those expensive components, because one resistor will cost you maybe $50. And then you make the prototype, and then you design the system, test it, again modify. When everything is working, you will make the engineering model with the actual components. And then you will do all the testing, vibration, thermal cycling, and all these testing. So there will be one more if you are in the aerospace or defense industry. Otherwise, you will make only one prototype, and then you will make your final one. For the DSO also, you will be using block levels, because we will give you the description. Then you will be designing input-output diagrams, block level diagrams, schematics, then board design. So you got a different input-output diagrams. See, your sensor input, then gain and signal conditioning stage, you got ADC, microcontroller, power supply, DAC, then filtering stage, amplifier. So that's the reason I said the DSO is a complex system, because it got ADC, it got DAC, it got CPLD, it got microcontroller, it got interface, SPI interface, it got complex front-end electronics. So DSO is a very good example, and DSO is a good system to master the system concepts. Then, so you know the design process. You will be getting the specification with respect to specification and budget. Then you will be designing the system. Then hierarchical design. So what do you mean by hierarchical design? Again, when you come to hierarchical design, means there are different types of hierarchical design. One is modularity and design reuse, then black box modeling, complex hiding, top-down design, well-defined interfaces. So hierarchical design is a symbol, like somebody told you don't know anything about oscilloscope. Then somebody said, I want to measure the waveform shape and I want to measure the amplitude. So can you make such a system? So that is called oscilloscope. Suppose oscilloscope didn't exist. Then you will be thinking, oh, the waveform, how can we get the waveform? You should be thinking like that. And then how can we measure the amplitude of the wave on a screen? So what are the required things? So then you will be thinking in terms of maybe some major blocks. These are the maybe some major blocks, front-end electronics, ADC, so and so. Then you again make it less complex. So that's a hierarchical design. That's called hierarchical design. Then documentation. As I said, engineering documentation is very important. What should be in it? What does it represent? Budget and specification or scope of the work. And then it should have the proper specifications and then scope of the work. Then it should have budget, bill of materials, schematics, schedules and deadlines. All these things includes engineering documentation. Specifications. So what are the specifications companies are looking into? So functional description, how the device or circuit is working, list of design features, budget, basic physical dimensions, sketches, then block level diagrams, then performance matrices like your test results, how we quantify them. Then bill of materials. So people ask you, do you have a BOM for your design? So bill of materials means you need the quantity, parts number, manufacturer, description, package type, rating, voltage, power rating, value, price, supplier, minimum order quantity. Then schematics. So universal language of the electrical engineer is the schematics, an essential step towards creation of any PCB, a reference for diagnostics and troubleshooting, a comprehensive description of signal flow. So schematics. So when I come to the lab, if I am there, I will ask you to explain the DSO, how the signal propagates in each block. Maybe you can take a schematics and then you should be able to explain how the signal is propagating. So that is a comprehensive description of the signal flow. So that will be definitely asked towards the end when you demonstrate. So bad schematics. So please don't make any schematics like this, because nobody can understand this one and reproduce. So a good schematics, I wouldn't say this is the best schematics. A good schematics means it should have the part number, it should have the pin, which one is the input, which one is output, So then resistor values you have mentioned here, which transistor, so that it can be reproduced and people can understand. So data sheet. So data sheets are your friend for this DSO. Understand your specific design requirements. Don't rely on one manufacturer for the information. Compare your components either using supplier online, parametric search, or data mining of data sheets. So these are the components comparison. Somebody did components comparison. This is done in the industry. So you can see diodes. Then they will be getting all the possible diodes. Then VR maximum, IR maximum, then peak values, and then what are the classes available, then comments. So sometimes your manager might ask you to make these type of comparison when you're designing a system, and then they will also add the price. Then they will pick up which one is the best. So design for manufacture. So design for manufacture also is very important. So when I come to this hierarchical design, I forgot to mention one more thing. So when you have hierarchical design, the hierarchical design is important. Why? Because you should be carefully designing your blocks. For example, in the oscilloscope, you got a ADC block that is doing the sampling. But then if something happens to the ADC, that component could be obsolete. And then you should be able to replace that components and make the block, and then that block should be able to fit into your remaining block without any modification. You know what I meant? So most of the time in the companies, when you design a system, as a system engineer, you should be careful. When other people come up with each block, then you have to think again. If something happens to components inside this one, then you will be replacing that component with a new one. If you are doing so, whether other people have to change anything. You know what I meant? So that is not good. In that case, that system design is not good. So that block should be kind of a semi-independent as well. If you are replacing some components, that should be solved within that blocks. Though that should not affect your input or output, so that other blocks need not be changed. So that also, as a system engineer, you should be careful. The design for manufacture. So components availability. So that is the first thing you should be careful when you design the system. Second, sourcing. So you should have always, if you are starting a company, then you should have a second sourcing. If these components are not coming, then you need another source. Then environmental consideration. So these days when you make something, people ask what are the environmental impact. So you can see in big companies, they have got sustainability officer. So they will be checking the sustainability of your product. Then the production cost. Then again the component availability and second sourcing. The second sourcing is very important if you are getting some help from other company, because we got one big company approached us because they lost one board in their system. It looks funny because they had some disagreement with their supplier, and then they were giving them a board, and then without that board they can't sell the system. It's a big company, and then they want to make the board. They asked us whether as a system engineer whether we will help them to make the board. So when we approach, it might be funny, but it is, they can't sell the system. So you should have a second, sourcing. Then working with others. So that is very, very important. So you can't work in an organization, especially as a system engineer, without working with others. In order to become a system engineer, you should work with others. As I said, you will be growing vertically in your area, then you will be going a T-type, horizontal growth. So how you will grow it? You have to interact with other groups, and then only you understand the system. So working with others is very important. If you, for example, this system, you should be working with the thermal people, because then thermal people will be handling the thermal requirements. Mechanical people who are making the housing. So you should interact, otherwise your structure, your electronics will not fit in. Optics people. Then, if you don't do that one, what will happen is kind of the railway. This is a very good example. If you don't have good communication, so it definitely will not match. Then working on complex systems often requires interaction with multiple design teams, which is true, with many individuals, each with their own specialization. So it is not that easy when you have a complex system to design, based on my experience. So the communication is very important. Also, people think differently when they come from a different background. So, well, I had experience, but when my PhD students recently started working on medical devices. Then what happened is when they interact with medical people, they think differently. They are correct, but they are not like engineers. And even their results are very interesting, because when I now we got lots of experience. So one a specialist called me to show some result. Then he said exciting result. Then I saw. Then when I saw some small dip like this, then for me that is not a result. I was as an electronics people, I was expecting some big waveform and then some peak. And then, but he showed me, that small dip, and then said that is an exciting result. And then he started explaining, how they got it. And yes, that is an exciting result. But then our background, makes some kind of prejudice to things. So that should, you should get rid of that prejudice as a system engineer. All the, people from different disciplines think differently. So you should be aware as a system engineer, otherwise you will not be able to integrate these guys together. So human factor design teams: forming, storming, norming, performing, and adjoining. So then you can definitely achieve a synergy with your group as a system engineer. That's what you should be trying to get. So when you have a group, even capstone is an example, as I said, because I take capstone as an example. And when you go for that capstone awards, if your project is shortlisted, they might come and ask, as a group, how did you work? That is one question often asked. So that question meaning is whether there was a synergy, or somebody else was driving, or all the three people were working together and got a synergy, so you achieved more. So that's the kind of answer people expect, and they can understand it from your project. So the synergy, as a system engineer, you should be able to achieve synergy from people. Like oscilloscope, again design, different people are developing different people are making different blocks, and then you should be able to get the synergy out of these people. Then only you will become a very good system engineer. Then supplier parametric search. So if you want to buy most components, electronics components, unfortunately in Australia you don't find a shop to buy all the components. Maybe you will find some in US and UK or in Europe, but here we have to buy most of the things from DigiKey. So if you need some components, most of the components you have to buy through DigiKey. Then element 14, or you can buy RS components, Mouser. We buy a lot from DigiKey these days. So this is a place where you should be able to buy. And then examples of embedded systems. So if you want to read more about recent embedded systems, so these are some links, just for your extra knowledge. Modern design teams. So these are some TED talks about modern design teams. Then again, if you are interested more about design for manufacture, that again is a big area. Then schematic symbols. If you want to study more about schematic symbols, this DGK. So these at the end I give you so many links just for your reference. If you are interested, you can further read on those. And we will not be asking anything from these links in the final exam. Then I think we are going to run out of time, and I will give you 5 minutes break before the next lecture. Then, so there are some frequently asked questions. The question number 1, do I need to take embedded system before taking the electronic system design? So my answer is no. You don't need to take embedded system. But then what are the advantages? If you did embedded system, you will be familiar with the Altium design. So that may be a good thing. And then you also may have got some experience with programming, which is not required for ESD. So you can take ESD without embedded system, provided you should be willing to learn Altium. We will be having Altium sessions, so you can catch up. Then LT Spice. How many of you did not use LT Spice? You did not use. Then it is easy. Don't worry. So LT Spice you can learn in 2 hours. Just to go to YouTube, there are so many links, and you can learn the LT Spice for learning the simulation. So if for those of you are not familiar with LT Spice, I would say today download the free version and then do some circuits. It's very easy, LT Spice. So because we will be doing front-end simulation using LT Spice. That you are designing some clamping circuit, amplifier, filter. So that is the first submission. So it is coming, but please, if you are not familiar, just download it and you can master it in 2 hours. I don't think more than 2 hours, you don't need it. Then if you are not familiar with Altium, you don't have to worry because we got all team. You will be designing some test board in the lab during the lab time, and then you are fine. Then you don't need to know any programming in the sense there is no programming in this subject because we don't have time. You will understand the DSO is going to be a big project, so we will give you the program for your microcontroller, but then we will not give you the program. You just will download it and use it, but you have to change the pin configuration. And then obviously I would love to ask you to write the code, but then the time is not sufficient. Most of the time we ran out of time in the previous years and held the lab after the exam for some students, because the fabrication, the mounting the components, it's a big project. It's more complex